Hello everyone, and welcome to Module 3, Chapter 3. In this module, we will be covering the subject of motion in the plane, or two-dimensional motion. When we say two-dimensional motion, we're really talking about mainly projectile motions. There are three topics in this chapter: projectile motion, circular motion, and relative motion. We will not be covering relative motion, guys, so keep that in mind, which is right here, determine relative velocity and so on. We're not going to be covering that, so you can just skip that part. So we're going to be only talking about two subjects: projectile motion and circular. And circular motion is really something like 10% of the chapter, or what we're covering. The bulk of the subject is projectile motion. So let's talk about projectile motion. So what is a projectile? A projectile is it's something that you throw. For example, let's say I have a stone in my hand and I throw it at a certain angle up in the air. This projectile or the stone reaches a certain height. We call it a maximum height, and then it falls, right? So it will follow, and the path that the projectile follows, we call it the trajectory, and that path is always a parabolic path, which what that means, it describes a parabola. So anyway, a projectile motion looks something like that. It is so let's say I'm on the ground. Here is the ground right here, and then I throw an object with a certain velocity, initial velocity, we're going to call it v0, at some angle theta. So what's going to happen is going to go up, and then it's going to fall down here, such that the path that is followed by the projectile, this path right here, describes a parabola. That's why we call it a parabolic path or a trajectory. Okay. So the distance from which the ball or the whatever object you're dealing with was thrown until it reaches the final destination here, we'd refer to this as the range. X, the symbol for it is X, the range X. Okay, and of course this is the maximum height reached by the projectile. I like to call it Y sub max, or capital H, or something like that. This is the initial velocity here, and again, this is the trajectory. Okay, how do we do a problem like that? The moment I throw the object up in the air, like here, the object becomes in free fall, just like with the subject that we dealt with. Remember free fall kinematics? So the object here is in free fall, and so what's happening is that it is gaining height here, but it is losing velocity. You see what I'm saying? It is losing speed, and that's why it will eventually stop. See, if it's not losing speed, if it's, say, gaining speed, it will just keep going up, 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 up. See what I'm saying? So it is losing speed. Eventually, the speed here becomes 0, and then the object falls, okay? But there is more to it than that. Here is how it works. I'm going to draw this again in a bigger picture, because I want to put some vectors there. So here is the, let's assume we are throwing it on a surface of the Earth like that, and here is the initial velocity of the projectile. Here is the angle theta, and let's assume it takes this path, this parabolic path, like that. So what's happening here is that, I'll take the angle just out for a minute. What's happening here, because this is the vector, and think of it like this is the x-axis right here, this is the y-axis like that. Okay, so this, this x component of the velocity will look something like this. This is v0x, and this is v0y right here, okay? Let me clean it up a little bit. This is v naught y. I'm going to put v naught right here, like that. Okay? And what's happening as the object is following this this trajectory or this parabolic path, what's happening, it's slowing down, but because g, the acceleration to the gravity, is in this direction, it's in the downward direction, and so the y component of the velocity is decreasing in value. You see what I'm saying? In other words, if let's suppose that the length of the vector for Vy is this long. This is the magnitude, this length, okay? When it is here, this length will actually get shorter, and then shorter again, and even shorter here. At the summit here, Vy becomes equal to 0. And that's why the object basically stops gaining height. You see what I'm saying? Because the y component of the velocity becomes equal to 0. But right after it passes the summit, which is right here, it will start, because now it's moving with the acceleration to the gravity in that direction, the downward direction. So because of that, you will see that the vector here is, the y component is gaining value, so it becomes bigger and bigger and so on. And by the time it reaches the surface, the surface of the Earth again, that value will be equal to the v naught y here. You see the symmetry there? You see what I'm saying? However, since there is no acceleration to the gravity in the x direction, there is absolutely no reason for v naught x to change. In other words, it will stay constant or the same all through the object's flight. So basically, if this is v naught x here, at this point here, it will also be v naught x, exactly the same vector, nothing happening, no gain or loss. V naught x. Also here, it's v naught x, and so on, all of them. Even here, v naught x. You got that? So that's basically how the velocity vectors are distributed all through the path. You got that? Okay. Now, since the velocity, so here we have basically two motions. One, we refer to it as horizontal motion. Horizontal, I'll write it down again. I like to call it HM. And then we have vertical motion, VM. Okay? Now, the vertical motion, which is basically in the y direction, and that's basically working with g or against g, depending on where the object is along the path. You see what I'm saying? However, horizontal motion is in the horizontal direction along the x-axis, where there is no acceleration in that direction. So in this case, and of course the velocity is constant, so if I'm going to measure the range of the projectile, which is basically what I showed you here, this range basically is related to the x component of the velocity. So the range x is equal to v naught x times t. See what I'm saying? This is an important formula to keep in mind when it comes to calculating the range of the projectile. How far did it go? Horizontally, that is. Okay? Where for the vertical motion, well, that's free fall, which basically we're going to be using the free fall kinematics. There they are. V equals v naught minus gt. I hope you still remember them. V squared equals v naught squared minus 2gy, and then y equals v naught t minus 1/2 gt squared. Now, to remind ourselves that all these velocities are in the y direction versus this velocity in the x direction, so keep in mind that you want to put in maybe a sub y here, because these are all in the y direction. Okay, you got that? Okay, so for vertical motion, we use those equations. Now, maybe 70% of the time, this, from my experience solving projectile problem, this equation would be sufficient for a lot of problems. Okay, I mean, you can pick any of them, they're all equivalent, doesn't really matter. But for most of the problem that you would be solving, I would say 3/4 of them would be, you will probably use this equation more than any other equation. Okay. All right, so that's basically how it's set up. So for you have HM and VM, horizontal motion, and since horizontal motion is not an accelerating motion, so basically we're just going to be using, the range is equal to V naught xt, and for vertical motion we use the free fall kinematics. Got it so far? Okay. Let me show you an example, show you how this works and how to apply all of that to some basic problems. I want to start with example 3.3 on page 74. Let me go there. 74. Right there, here. Let me make it a little bit bigger. Too big. All right, so you have this picture. This is a paintball gun. You got this boy shooting with his paintball gun. So it says here, now we are going to look at a classic example of projectile motion, a bullet fired from a gun as shown in this figure 13. I'm not sure it's a picture or, yeah, okay, the picture. All right, it says a paintball is fired horizontally at a speed of 75 meters per second from a point 1.5 meter above the ground. Okay, here's the diagram. I would rather look at the diagram. So here's the gun. It is fired horizontally, which means there is no initial Y component. You see what I'm saying? So here is the horizontal component, and it is 75 meters per second. The height of the gun is 1.5 meters above the ground. The ball misses its target and hits the ground some distance away. Okay. A, for how many seconds is the ball in the air? Basically, he wants the time of flight. And B, find the maximum horizontal displacement, which is basically the range. Here we go. He said we will call that the range. And we're ignoring it. So he wants, what is the time of flight? The total time of flight of the ball, and what is the range of the ball. Okay, so let me show you how that works. Three point three. So what you have in here is the height, and the gun is somewhere here, right? I don't care for the gun. I'm not going to draw the gun. I'm just going to draw, say, the bullet. Here it is, and it is moving horizontally with V naught. That is the height of the gun or the bullet initially, 1.5 meters. Keep in mind that's a negative answer, right? This is the negative Y because it is below the ball, and the V naught here is 75 meters per second. Since it is horizontal, so that means this is V naught X, where V naught Y is equal to 0. I'm going to give you another example where V naught Y is not 0. But this one is a simple problem. Okay. So what's going to happen is that the bullet is going to follow a parabolic path, and then it's going to fall somewhere, let's say here. So that would be the range X. See what I'm saying? And there we go. We have this diagram, and he's asking for the time of flight, the total time, and X. Okay. Again, like I told you, you divide the problem into two parts. One, horizontal motion, which is X equals V naught xt, the equation that I just showed you. And like I said, by default, your default equation for the vertical is this one. Like I said, 70% of the time it works. Other times you may want to, choose other ones. One of the three here, or the other two rather. So let's start with our default equation. Y equals V naught yt minus 1/2 gt squared. And what you want to do, once you put in the horizontal motion and vertical motion like that, always set it up like that. Start always with like this. Then you put in your numbers, and then see if you can solve them simultaneously together somehow. Okay? So let's start with the horizontal motion. I don't know X. I mean, he's asking for it. I do know V naught x, which is 75, times t. He's asking for t as well. So I have two unknowns, one equation. This equation is not going to help me much, so I just leave it on the side right here. And now I come here, okay? So what is y? Well, y is the height. Oh, okay, when I say y here, basically it is the height from which the ball was thrown, okay? So in this case, the height is basically 1.5. Since it is below the ball initially, that will be negative. So in this case, I'm going to have negative 1.5 equals to, now what is V naught y? Well, we just said V naught y is 0. Why? Because he said the ball was thrown horizontally, and therefore, let me write it down again here. V naught y is equal to 0. Okay, this is given to us in an indirect way. So in this case, this whole thing goes to 0. So I'm left with negative 1/2 gt squared. Aha, now look at that. As you can see, I can solve for t. I'm basically done with the problem. I can see how this problem is going to be solved. So anyway, the minuses cancel out. And so that's 1.5. Half times 9.8 is 4.9. I hope you memorize that by now. And then therefore t is equal to 1.5 over 4.9 to the power of 1/2. Is that right? And then we would calculate that. I have my calculator with me here. I hope you are calculating with me. And we would calculate that. That would be 1.5 divided by 4.9 to the power of 1/2. And that's equal to 0.5. I'll write it down here. So the time here is equal to 0.553 second. There we go. This is the total time of flight. Okay. Now we come to the range now, right? Well, the range is x equals 75t. I have the t already. So the range in this case, 75 multiplied by 0.553. So multiply what I got by 75. The answer is going to be 41.5 meters. And there we go. So in other words, the projectile, here is the projectile. The time of flight of the projectile is 0.553 seconds, almost half a second or so. And then the range, how far it's going to go and hit the ground here, it is 41.5 meters. Simple enough? Okay. Let me show you something else. Before I do another problem, I want to talk a little bit about the height. The height here for projectile motion is a little bit complicated, this y right here. I'm going to talk a little bit about it here. Okay. When you work on projectile problems, you will notice that they are classified, it's one of the four, okay? It's one of the four projectile problems. Here's how it works. The simplest of all is that it is, think of it like from surface to surface. You hit the ball or whatever, bullet, whatever, at a certain angle. Here is the initial velocity, and then it falls to the ground, to the floor. As you can see here, it starts from the ground and back to the ground. We can call it surface to surface projectile. So in this case, the height y is 0. There's no height. In other words, if I'm going to be using this formula, this y is 0 if I am dealing with something like that, because as you can see, there is no height. You got it? However, look at this one. If I have something like this where I throw it from a height down to the ground, which what we did, so here we're starting with some height, okay? And this height, we said it's negative. Why? Because it is below the projectile, below it, remember? If it's below it, remember they have x and y like this, and this is the negative side of the y-axis, and therefore this is negative. You got that? Okay, so this one we can call it, we'll call it surface to surface, okay? And this one we can call it air to surface. Again, those terms are my own, they're not formal or anything like that. Air to surface. And then we have another one. Imagine that you have, let's say, you have a slingshot or a gun or whatever, and then Oh, another idea. Let's say Romeo is here and he throws a bouquet of flowers to Juliet, who is on the balcony. So here we're starting with, here is the velocity, here's the angle of projection, and it goes up like that. See that? So here, this is the height. See the difference between this height and this height? What's the difference here? This one is surface to air. See the difference between the two? What's the difference? Okay, so what is the value of the height here? Is it negative or positive? It's positive. Why is it positive? Because look, this is the x-axis, here is the y-axis, and it's not below, it's actually above right here. So it's above it. So this one is actually positive. Got it? Okay. And the last kind, imagine a basketball player, okay? Here is the basket right here. Okay, here's the basket. And here's the basket. So the basket is to some height way down there. Okay, and we have a basketball player. Here he is. Here's his arms. That's the ball, right? And he's going to throw the ball to the basket like that. You see what I'm saying? So he's starting with some height. We'll call it y1. Okay, the height of the ball. And then the ball is going to go to the basket. Let's say that the problem we want to know up to here. So that will be, we're going to call it y2. So here we have two heights. Well, what is the height then? If I'm going to use this equation, so what is this height in this case? So I'm saying, what is the height? Well, the height is basically the difference between them. The difference between the two. Why? Well, this height is basically the net between them. Okay? So let's assume this height is, say, 15 meters. Okay? And then this height, let's say, oh, that's too high. Hold on. Let me be realistic. Let's say this height is, let's say, 4 meters. I think it's a little bit less than that. And let's say the height here, let's say 3 meters. Okay? I think it's too high. But anyway. So what will happen, this height, we talked about it, is what it is below. See that? It's below. That's the negative y-axis. So this must be below the y-axis. So that must be negative. And this height is from here is above the above. So that makes it positive. So what you want to do is that you take the difference between them. 4 minus 3 equals v naught yt minus 1/2, whatever you got in here, you know what I mean? But basically you take the difference between them. You got that? So you take the difference between the positive one minus the negative one. Basically what you're doing is you're getting the net height, which is right here. See that? That's the net height between the two. And that net height is, as you can see, it's positive. It's above the ball. Okay, and that's why this number is positive. You got it? Okay. All right, back to some problems here. Let me see. I think there is another good example in the book. Oh, yeah, this one is a really good example. Example 3.4. A little bit long, but it's really educational. So please pay attention to it. 3.4. Oops. All right, let's go back to the book. Page 75. Oh, okay, it's just the next page. All right, it says here, all right, so he said, now let's consider a projectile problem in which the initial velocity, it's right here, there's the initial velocity, is specified in terms of the magnitude and an angle. Okay, so we have the initial velocity. As you can see here, it's no longer like the example 1. It's not horizontal. It's some initial velocity with some angle. Okay. It says, suppose a home run baseball is hit with an initial velocity or speed of V naught equals 37 meters per second. All right, at an angle of 53.1 degrees. Okay, so we have the angle of projection, that is 53.1 degrees. All right, so of course the ball is going to follow this parabolic path until it falls here to the ground. Find the ball's position and the magnitude and direction of its velocity when t is equal to 2 seconds. In other words, let's assume what that means is this. Suppose, for example, let's say it took the ball, say, 3 seconds until it hit the ground. I don't know how long, but let's just say 3 seconds. So on the second, suppose the ball is right here. Okay, suppose it's just right there. Well, what's the velocity of the ball here, the x component and the y component? What's the height of the ball here? And how far did it go horizontally, the range of the ball right there? That's what he's asking. Let me repeat the question again. Find the ball position, which is x and y, and magnitude direction, basically, and the velocity component, x and y of the velocity, and their magnitude, which is Pythagorean, at the second. Okay? It's a big question. It's a very long question. Okay. B, find the time the ball reaches the highest point of its flight, basically right here. How long it will take the ball to reach the maximum height, and find its height, and also find y max, what he calls h. Okay? And C, find the horizontal range. So we want to also find the total distance traveled by the ball horizontally. He says find the horizontal range r, and that's it. Okay? All right, let's do it. So I'm going to draw that first. I'm going to show you how to solve a problem like this. Always draw a free body diagram. It will really help you solve a problem. It's very, very important. So here is my FBD, free body diagram. So I hit the ball like that. Goes up, and then down here. Here is the range. Here is the angle of projection. Here is V naught. So V naught, he says, is equal to 37 meters per second. You can see it on the side of the screen. And angle here is 53.1 degrees, right? Before I do anything, I need to resolve this vector, V naught, into x and y components. Okay? So let's do that. If you don't know why, that's okay. Just bear with me. So I need to find V naught x, and I need to find V naught y. This is very important. That's the first thing you do. So it's going to be V naught cosine 37, and that will give me cosine 53 rather, 53.1. So let's see, we have V naught is 37, right? So I have 37 times cosine 53.1, answer 22.2 meters per second, and V naught y is 37 sine 53.1. So I have 53.1, what am I doing? Sine 53.1 times 37, I'm using my calculator, 29.6 meters per second. There we go. I got those. Those are very important. So I'll just leave them, box them, leave them on the side. And now, what I want to do is I want to divide the problem into two components, horizontal motion and vertical motion. Okay? So what do I know? Well, I know the horizontal motion is the range x equal what he calls big R. X equals V naught xt. And the vertical motion, again, by default, this is the equation that I'm going to be using. V naught yt minus 1/2 gt squared. Okay? What is the height? What's the height of the projectile based on this one? It's 0, correct? If I want to find the total time traveled by the projectile based on the information given to me, for now I'm ignoring what he's asking for. Okay, I'm just going to do something else here for now. Let's suppose he's asking, what is the total time traveled by the baseball? Okay, I can use this. Do I have everything? I think so. Look, y here, which is either the initial height or the final height. If the initial height is negative, the final height is positive. But either of them, it's really 0 because it's kind of surface to surface. So that would be 0. And I can find the total time. Again, he's not asking for it for now, but I'm going to do it just for the sake of explaining things here. So total flight time of the ball so I have, go back to that, it's going to be 0, right? No height. And that's going to be v naught y, look at it right there, right? So I have here, but let me just write it down symbolically. I like to solve things. I like to do the algebra first. And that will be, let's make it 4.9 t squared. Is that right, guys? Now, if I take t as a common factor, v naught y minus 4.9 t equals 0. As you can see, this t will go away. Just divide both sides by t. And then I'm left with the total time really is v naught y over 4.9. If I didn't make any mistake. Oh, I think I missed. Oh, no, I didn't. I think it looks fine. So if I do that, I can tell you what is the total time of flight. Well, v naught y, I just got it right here. V naught y is 29.6, right? So I'm going to plug it in. Divided by 4.9. And that will give me, let me use my calculator, 29.6 divided by 4.9, answer 6.04. So I have here 6.04 second. This is the total time of flight. Got it? Okay. Now, do I want to know the range? In other words, how far did it go from here to here, this range? Well, I can use that. This x is really r, right? See what I'm saying? You can call it big R if you want to. So in this case, I have big R equals v naught x t, and t I just got, which is right there. This is the one right here. So I'm going to plug it back in here. So I have here the range, v naught x. Again, I have it right there, right at the edge of the screen from the top, right there. So I have here 22.2 times 6.04. And I'm going to use that, I'm going to calculate that times 6.04. Answer 134.1. 134.1 meters. There we go. So the ball went this much distance, or it fell 134.1 meters away. You got it? Okay. All right, now let's go back to the problem. He says, go back to part A. He said, find the ball's position and velocities, x and y, at the second. Remember, so here, look at that. The total time is 6.04. So on the second, if I'm going to guess, it's probably somewhere down here. See what I'm saying? I mean, this is since it's symmetric, probably at the third second, it is right at the summit, roughly, give or take, more or less. And the second somewhere here. So he's asking for what is the speed, x component of the speed, y component of the speed, the range, how far did it go horizontally, and the height of the ball here. Okay? Kind of sounds like a tough problem, but it's not really. You got that? Okay. So how do we do it? Well, let's start with, so at, maybe not, use at t equal 2 seconds. Well, the range in this case is just going to be v naught xt. Remember, the range is no acceleration in the horizontal direction. So it's just going to be that. V naught, if you go back, it is equal to 22.2 multiplied by 2 seconds. He said that 2 seconds. So in this case, it will give me the range. How far did it go? And that will be 44.4 meters. There we go. So after 2 seconds, the ball has already traveled this much. You see what I'm saying? Okay. Now he wants to know how high is it? In other words, let's go back to the picture. So let's assume the second is right here. So the distance traveled, horizontal distance from here to here, is 44.4. And what is the height? This height right there. Okay, this height. Assume the ball is here. What is that height? Well, again, I can use the same, that same old kinematic equation that I just told you to use, which is this one, is v naught y t minus 1/2 gt squared. Now remember, this time we already have a height coming. You see what I'm saying? We have a height. So it has already gained height. So this y is non-zero anymore. So that's going to be 29.6 times second minus 1/2 times 9.8 times second squared. And then I'm going to calculate that. So 29.6 times 2. Again, I hope you're working with me. I'm going to get here 59.2 minus, this is 4.9 times 4. 4.9 times 4, answer 19.6. And then 59.2, answer 39.6. So it's 39.6 meters. Okay, so the ball, go back to the picture, at the second somewhere here, the ball is at the height of 39.6. Got it? Okay. Now the second part of the question, part A, he said, what is the velocities? In other words, what is the x component of the velocity and the y component of the velocity? Remember I told you from that diagram, the velocity, the y component of the velocity changes all the time because the g is in the vertical direction, but x component of the velocity does not change. So what is the velocity in the x component? Well, it's going to be the same. We just calculate to be, 22.2. And that thing, this 22.2 for Vx, does not change until the ball hits the ground. Got it? But this one changes, the Vy changes. This is only the initial velocity. But everywhere else here is different. You got that? Why? Because there is a g. There is a g factor here. There is gravitation. The gravitational effect, or acceleration due to gravity. So, V sub x is really equal to V naught x, and that's just 22.2. Does not change. Okay, invariant. If you want to use a invariant, it's a good word to know. Does not change. Not opposite of constant. Invariant. Okay, Vy. What about Vy? How do we do that? Well, one way to do it is we go back to one of the kinematic equation. I would recommend the first one. You can use the second one, is fine. I like the first one. The first one says Vy equals V naught y minus gt, correct? And I think we got everything. Just plug it in and you'll get Vy. So V naught y, which is equal to 29.6, is that right? Minus 9.8 times 2, and there we go. So we have 29.6 minus 19.6, and that will give me 10 meters per second. There we go. Okay. Now the last part, as far as velocity is concerned, he said the magnitude and direction of the velocity. Okay. So you want to find the magnitude. How do you find the magnitude, guys? Remember, V, the Pythagorean, is equal to V sub x squared plus V sub y squared, and I got them both. V sub x is right here, and V sub y is right there. I'm just going to plug them in there, and that's going to be equal to square root of 22.2 quantity squared plus 10 quantity squared. And then when I do that, I have 22.2 squared plus 100 under the root, and that will give me this. The answer is going to be 23.3. I hope I did it wrong. I did not do it wrong. 24.3 rather, meter per second. This is the magnitude. Nope. Now the direction of that velocity. How do I find the direction? Go back to vectors. Remember the vectors? Phi, the direction will be tan inverse of v sub y over v sub x. Remember that? We talked about that in chapter 1. How do you find the direction of a vector, a resultant vector? So it's just going to be tan inverse. What's vy? It's 10 over 22.2, and that will give me tan inverse of 0.45, and therefore the direction, remember direction is an angle basically, is 24.2 degrees. There we go. So I found the magnitude and the direction. Okay? Okay, good. Now we come, this is all part A. Now we come to part B. He says in part B, find the time the ball reaches the highest point of its flight, okay? And the maximum height. Okay, so we want to know the maximum height reached by the ball, and how and when does the ball reaches the maximum height, the time. Okay? Well, how do we do that? There are several ways to do this problem. First of all, let me find the time the ball reaches the maximum height. The question is, what's going on at the maximum height? In other words, let me answer this question. Why the ball stops gaining height at the maximum height? Kind of a silly question, but why? Why it stops gaining height? It stops gaining height because v, the velocity in the y direction, becomes 0, not the x. That's why it keeps moving forward in the horizontal direction, moves forward, but it stopped gaining height because vy is 0. You get that? So at maximum height, at max height, ball has v sub y equals 0. But v sub x is the original, v not x, invariant, doesn't change, right? So what is that? How does that help us? Well, let's go back to kinematics. Pick one of them. Let's pick the first one. I like the first one because it's just simple, it's linear. So I have I have v sub y equals v naught y minus gt. At maximum height, this thing is 0. So therefore, the time the ball reaches the maximum height, just solve for it. So you get v naught y over g, and that will give me v naught y. I got it to be, if you scroll back up, what is it, 29.6, I think? 29.6, that's right. So I have, I hope you're looking at your notes, 29.6 divided by 9.8. And I calculate that. It's got to be around 3. How do I know that? Because the total time of flight, if you remember, is 6 point something. So it's got to be around there. So that's going to be 29.6 divided by 9.8. Answer 3.02. Okay, so we have here the time is 3.02 seconds. You get that? So at almost at the third second, the ball reaches the maximum height. Now the next problem is, the next question, he said, what is the maximum height? Well, there are two ways to do it. Okay, let me show you both of them. Start with the second kinematic equation, this one. (2gy), right? Remember that? Okay. What's going on at the maximum height? Vy is 0. Once I make this 0, this immediately becomes a max, because it's only 0 at the y max. And there we go. I can just solve for y max. You see what I'm saying? So that's y max is equal to v naught y squared over 2g. You see how I did manipulate the minus signs. And then we'll plug it in. So we have here 29.6 quantity squared divided by 2 times 9.8. And then when I do that, use my calculator. So I have here 29.6 squared divided by 19.6 Answer 44.7. So here I have y max is 44.7 meters. See what I'm saying? Here's another way of doing it. I'll use the good old kinematic equation, the one we use all the time, the default one. Y equals V naught yt minus 1/2 gt squared. Again, this one comes in really handy. And what do I have here? And remember, I already know the time of reaching the maximum height. See what I'm saying? So, which is 3.02 right there. So I can just plug it in here, and that will give me the height at that time, which is what the maximum height, and I should be this number. So let's try it. So it's going to be 29.6 times 3.02 minus 4.9, 3.02 quantity squared, and you calculate that, and if I calculate it, 29.6, can you do it in one shot? 0.6 times 3.02 minus 4.9 times 3.02 quantity squared. Answer 44.7. There we go. See that? So that's another method of doing it. And then the last part of this problem, part C, it says find the range of the, oh, we already did that, right? This is like when we did it very beginning, when, there we go. Remember the range? You said the range is 134.1 from that. So I guess this part really, when we did it, that's really part C. See what I'm saying? You said find the range. Remember we did the total time of flight using the same equation, this one. Total time of flight. We got the total time of flight is 6.04. And then you plug it into the range equation, and that will give you the range, okay? See above. I hope you've been taking notes so you know what that means. Okay, good. Next. Okay, I want to move on to the, maybe I'll do another projectile problem from the homework, but for now I need to move on to the next topic, which is the last topic, and the topic is very short. If I was writing this book, I wouldn't put it there. I would just put it in its proper place. So there is a whole chapter on circular motion. I don't know why he shoved it in here. I have no idea why. But anyway, so here it is. I hope this chapter is going to be a little bit lighter than the previous one. Circular motion. I mean, circular motion is a very big subject, and we're going to deal with it probably 2 or 3 chapters that's just on circular motion. So it's a very big subject. We'll talk about that in details later on during the semester. But the only thing we're talking about here is that if you have an object that is moving in a circle, okay? Let's say, for example, trying to think of something. Well, let's take a top view. Let's say you're looking at a top view of someone, of a driver of a car driving on the highway. Like, let's say that you are driving on the highway and the highway is curved. So here is a top view how the highway looks like. Let's say something like that. So you are, remember when you go like trying to make a U-turn or something like that, and here's the car, and you are moving with some velocity v, say 55 miles an hour or something like that, okay? And this is the radius, let's call the radius of curvature. This is the radius in which you are taking, okay? This is the radius. So what's happening with you here is that, see, at this instant, here is the direction of your speed or the velocity. Here, Here's you are right here. Look at the direction of your velocity, and here, look at the direction of your velocity, and so on. As you can see here, your tangential velocity, if you will, is constantly changing direction, okay? So as a result of that, remember when we say that if the velocity is changing, whether direction or magnitude or both, that means you will have an acceleration, okay? What is acceleration? Change of speed. Well, change of speed in terms of magnitude or change of speed in terms of direction. So here when you're going around a circle or a curvature like that, as you can see, the direction of your velocity is changing constantly, and therefore you will have an acceleration. Okay, so we have an acceleration. And this acceleration is a special kind of acceleration. We refer to it as the centripetal acceleration. We'll deal with it later on in details with forces and so on. And this centripetal acceleration, I think your book calls it what? Oh, okay, he calls it for now the radial acceleration. Okay, radial acceleration, but it is centripetal because in the direction of the radius. I'll come back to this in a second. And this centripetal acceleration is equal to the velocity of that object going around the circle squared divided by the radius of curvature of the circle. Okay? Again, he calls it radial. Okay? Let me show you a better picture of this. So here is, imagine you have, say, the electron going about the proton in the hydrogen atom, or the moon going around the earth, or something like that. So here is one object, here's the other object here. And we're going to ignore the object in the center, okay, for now. So I'm just going to concentrate on the orbiting object, say the electron. It's going around, this is the velocity, this is the radius right here. And what's happening here as it goes around in a circle, like that. So what's happening here, take the R away, what's happening, you will have that acceleration, this radial acceleration. And the direction of this acceleration is actually toward the radius, toward the center, like that. It's in the radial direction. I can't draw that. Hold on. I'm trying to be. There we go. There we go. Okay. So that's the radial acceleration. It's always toward the center. That's why the meaning of the word centripetal means center-seeking acceleration, toward the center. And this acceleration is equal to the velocity squared divided by the radius of the circle, or the circular path, whatever it is. Okay, R. Got it? Simple. Okay. Let me do a problem for you to show you what that means. That's it. That's, believe it or not, this is just basically the whole topic of circular motion. And so he has two examples. I'm going to do example number 3.9. And then there are, I think, 2 or 3 problems in the homework on that. I'll do a couple of them. There are 3 of them, actually. So I'm going to do a couple of them. So, 3 problems, that should do it for you, for those, as far as circular motion is concerned. Let me go back to the book. I'm going to do example 3.9, page 8.3. 8.3. There we go. Let's read it together. He says, in this example, the motion is in vertical circle. So we have a vertical circle like that. Passengers in a carnival ride travel in a circle with radius 5 meters. Okay, so the radius of the circle is 5 meters. The ride moves at a constant speed. Now, it doesn't mean the constant velocity because it's changing direction, remember? At a constant speed, and makes one complete circle in a time 4 seconds. Okay, this big T we call it a period. What is a period? A period of the time it takes to complete one cycle or one circle. Okay, so we call that the period. And I like to use the Greek letter tau rather than big T. But anyway, now he's asking, what is the acceleration of the passengers? Okay, simple problem. So what I have is this. So here is the circular path of the passengers like that. Okay, and let's say, I'll just match the picture, so you put them there. All right, so here is the passenger right here. I'm going to take just one passenger. Here is the radius of the circle. and it's moving in that which direction? Clockwise? Counterclockwise? Okay, clockwise. All right. So we're going to assume it's moving in this direction. It doesn't really matter, up or down. So there we go. This is v. Okay. So the acceleration is going to be this way. Remember I told you? It's center seeking right there. Toward the center, is always toward the center. And the radius is equal to 5. All right. So the acceleration is equal to v squared over r. Right? Okay, I know the r. He wants a. Well, how do I find v? See what I'm saying? So how do I find v? Well, here's a trick for it. To find v, basically v here is distance over time. What is the distance traveled here? Well, the distance traveled from v all the way back here. That distance, well, that would be the circumference of the circle, right? 2 pi r divided by how long it takes it. Well, how long it takes it? It's the period, tau. You see what I'm saying? This is a very important formula to keep in mind when you want to find v, velocity, and you're dealing with circular motion. Not just this chapter, in the future. Always keep this formula in mind. It's a lifesaver. It will help you find that velocity. The magnitude of it, the speed. So it is basically the circumference divided by the period. Okay? So, and I have everything. He gives you the period. He didn't give it to me for nothing. He actually gave it to me because I want to use that formula. Help me use it. So v equal to 2 pi times 5 meters, divided by the period. He said, look, the ride moves at a constant speed and makes one complete circle. One complete circle. That's a period. That's a cycle. In 4 seconds. Get that? So that will be 4 seconds. And there we go. You just calculate that. So it's going to be 2 pi, which is 6.28. 6.28 times 5 divided by 4. Answer, 7.85. So the velocity is 7.85 meter per second. Okay? That's it. I'm basically done with the problem. And then the next part, we'll find the acceleration right there. And that's v squared over r, and that'll be 7.85 quantity squared divided by 5 squared divided by 5. Answer, 12.32, 12.3. So the acceleration is 12.3. And what's the unit on it? Meter per second squared. Don't forget that. That's the unit of acceleration. Got it? Okay. Okay, next, let's do something. I'm done basically with the chapter. Again, please, we're not doing relative velocity in a plane, okay? Let's do some homework. The homework problem that we have, let me show it to you for mastering. This is mastering 151. All assignments are there. Oops. I need to log in again. There we go. Chapter 3. Zero student completed. I hope you know that all the homework of until the end of the semester are all available for you. If you want to work ahead of schedule, that'd be fine. Anyway, these are the homework. Problem 14, 20, 51, 56, 28, 31, 33, and 22. Okay. I'm going to do, which one did I think about? 28. I'm going to do 28. Simple, very simple problem. Let me go to the problems. And, 33. I want to do 28 and 33. I think we'll call it a day. I'm not sure. You're more than welcome to ask me and or ask the professor if you have any, issues with those problems. But I'm going to do 28 and 33. I'm both really easy. They're not very difficult at all. But anyway, so let's start with number 28. Let's go to the book. Again, I go to chapter 4 and then I go backwards. Oh, I know the page number. I don't need to do that anymore. I do that for some books that don't have that, you know, you can't put in the page number. Some books don't have that feature. It's kind of cool, but some books under mastering, that is, they don't have that feature. Yours does. Anyway, go backwards. Number 28. Right there. It's level 1. Pretty simple. It says you swing a 2.2 kilogram stone in a circle of radius 75 centimeter. Okay. At what speed should you swing it so its centripetal acceleration will be 9.8 meters per second squared? Simple, huh? So, okay. How do we do it? Well, we said that, he said that the radius is what? 75. Whoops, I put in something. How do I go back? Darn it. That was dumb, what I've done. I think I can go back this way. No? Okay. Sorry, I'm going to have to do it again. All right, let's just go. I clicked something. I don't know what. Anyway, page 91. There we go. Let's try not to click anything. There it is right there. Oh, I clicked that. But how do you go back when you click? I don't know. Whatever. Okay. So he said the radius is 75. And the mass is 2.2 kilogram. Not even sure if it's important, the mass, for now. And he wants what would be the speed, he said, if the acceleration is 9.8 meters per second squared. Okay? So, pretty simple problem. A equals v squared over r. Therefore, v equals ar under the root. And you just plug it in, right? That's it. So, just square root of 9.8 times the radius 75. And then we calculate that, and you'll get the answer. Simple. Number 33. This one is kind of interesting. I like it. I've done it before. You find it in just about any physics book. People like it, I guess. It's called the pilot blackout in a power dive. Okay, so here is the diagram. So you have this jet plane right here, and it's going in a nosedive down and then up like that. He says a jet plane comes in for a downward dive as shown in the figure. The bottom part of the path is a quarter of a circle. So this part is a quarter of a circle having, let me get it bigger, having a radius of curvature of 350 meters, okay? According to medical test, pilot lose consciousness at an acceleration of 5.5 g, okay? If it's 5.5 g, you lose consciousness. At what speed in meter per second and miles per hour will the pilot black out for this dive? You got it? Okay, so how do we do it? Well, let's draw the diagram. So it looks something like that. Here is the dive, if you call it, and here is the pilot. It's going in that direction, like this, right? And this is a quarter of a circle. He said it's a quarter of a circle. It looks like a more than that, but anyway, let's assume it's a quarter of a circle like this. If I can do it with a circle, there it is. Here is the pilot with this velocity, radial direction, and of course the centripetal acceleration is in this direction, like that. Okay, and he says the acceleration is 5.5 g, right? What does that mean? It means 5.5 times 9.8. That's the value of the maximum acceleration before the pilot loses consciousness. You got that? All right. So he's asking, what is that velocity that corresponds to that? You got it? So A is equal to v squared over r, and he said the radius of that curvature is given to us. Did he give it to us? I think he did. Back. Jet plane. I thought he did do this. Yeah, there we go. The radius of 350 meters. Okay. So the radius here is 350 meters. There you go. Okay. How do we do it? The first thing I need to do is to find, he wants to, the first thing is just basically solve for V. I was thinking of something else. V is equal to AR under the root. Is that right? And what's A here? 5.5 times G, which is 9.8, times R is 350 under the root, and that will be 137.3 meter per second. Got it? The other problem that you need to do is number 31. I believe this is homework, number 31. So I'll leave it for you to do it. It's level 2, a little bit harder, but it's not really that bad. And I think I'm going to stop here, okay? So please let me know if you have any questions, and have a good week. Bye-bye.